So, welcome all of you for today's class. In the last class, we discussed extensively about coupled spin system. We understood the difference between strongly coupled and weakly coupled spin system, and also I discussed a lot about Popple nomenclature. In the sense, when the spins are strongly coupled or weakly coupled, it can be characterized by certain notations. For example, weakly coupled, it is called AX, AMX, AMPX, etc. Whereas strongly coupled spins are identified as AB, ABC, ABCD, etc. Where for strongly coupled, the characters or the alphabets next to each other is defined. Whereas for the weakly coupled, the alphabet which is far away in the alphabet order is taken into account. So, then it will become weakly coupled, alphabet next to each other are called strongly coupled. That is how it goes. And I took several examples to discuss what are example of strongly coupled spectra, weakly coupled spectra, molecules where strongly coupled, which are strongly coupled and weakly coupled. When there is chemical equivalence, I said we can use prime notation. When there are groups of spins, chemically equivalent like CH2, CH3, etc., we can use subscript notation. That also we discussed. And then we took a special example of 2x case, a 2AX spin case. In the case AX spin, I showed we can work out by using the writing down the Hamiltonian and diagonalizing the matrix, get the eigen values, we can get eigen frequencies, we can get the frequency of transition. I got 4 frequency of transition for 2 coupled spin system, and then we can get the transition difference in the frequencies between different as per the selection rule. We found out there are 4 transitions in weakly coupled 2x AX spin case where 2 for A and 2 for X are there, and from the center of the chemical shift each peak moves on either side by J by 2. That is what we understood. And I said for a weakly coupled spin case, or when two coupled spins are there, you can get maximum of 4 transitions. Let us continue further today and see what is going to happen. We will now consider the example of n coupled spins. For n coupled spin, there will be a total of 2n minus 1, 2nc n minus 1 transitions. For example, if I take 3 equivalent coupled spins, we should get 6C2, that is 15 transitions. If there are 4 spins, maximum we should get 56 transitions. Of course, by a first order approximation and by a family approach, we have been discussing. I said for 3 spins are there, each spin will give rise to 4 transitions, there could be maximum of 12. Why then 15 is coming into the picture? Remember, once I said there are combination transitions, for then there will be 3 more transitions which does not give information about the chemical shifts, which comes at some difference of the chemical shift. J coupling information may not be possible to get from that. Similarly, 4 spin also we have maximum of 56 transitions, and most of these transitions are highly redundant. In the sense, for example, if I take 3 spin, there will be 12 transitions, and each spin will at the site of chemical shift of each of them there will be 4 transitions, and that gives you 2 coupling information. We have maximum of 3 couplings, but in each chemical site we can get 2 coupling information. That means there is redundant information. So, single quantum NMR spectrum are generally highly redundant. So, only few of the transitions are just sufficient to get the chemical shift and J coupling information. So, this is a typical example of an AX spin case where chemical shift of A and X are like this, and the J coupling interaction is 5.77 hertz. And if you take the ratio as per the ratio which I was telling, it is about 50.8. Clearly, it is a weakly coupled AX spin. We get 4 peaks of equal intensity, but still you see there is a small intensity difference. You do not have to worry about that deviation. Still it says there is a minute strong coupling character is there, but for all practical purposes this can be treated as a weakly coupled 2 spin case. A realistic example is like this, where a molecule like this is there, and you can see 2 transitions here for X and A. In principle, they are not of equal intensity. In principle, they have to be equal intensity. I consider a hypothetical example of an AX case for a heteronuclear spin. Here, proton and fluorine are taken into account. Mind you, proton and fluorine peaks will not come at the same frequency. They are coming at different frequencies, that we know. Proton in the 500 megahertz spectrometer resonates at 500 megahertz, whereas fluorine resonates at 470 megahertz. Just for the sake of illustration, both of them are plotted in the same graph. This is proton, this is fluorine. You see theoretical plot, all of them all the lines are of equal intensity. This separation gives you J coupling between proton and fluorine. Again this separation gives you coupling between proton and fluorine. This is a typical example of a hypothetical AS case for a heteronuclear two coupled spins. And each peak can be assigned to a particular transition. For example, we have been discussing earlier also 1, 2 and 3, 4 transitions correspond depending upon the selection rule. We can find out 4 eigenstates we got, we can find out the frequency of transitions. 1 to 2 and 3 to 4 correspond to, for example, AX transition, and 1, 3 and 2, 4 correspond to A transition. This is X transition and this is for A transition, and easily we can assign that. And if you going further, we have another example of strongly coupled two spin is AB. Earlier it was AX, now it is AB. As I said, the two letters are close in the alphabet, means they are strongly coupled spins, and in the case of the strongly coupled, chemical shift A is not equal to B, that is they are two different chemical shifts, but delta delta difference in the chemical shift is approximately equal to J coupling, and J coupling is non-zero in this case. And if you think of a strongly coupled spins, two spins, you cannot get heteronuclear because the chemical shift separation is of the order of megahertz, several megahertz compared to coupling of the few hertz. As a consequence, heteronuclear AB spin system is impossible to get. You always deal with only homonuclear AB spin system. Now, how does the spectrum come? This is how the spectrum appear. A hypothetical AB spectrum plotted, and you see two central lines are of equal intensity, two outer lines are of equal intensity, but all the 4 lines are not exactly equal, unlike what you see in the AS spin case. But of course, there will be always a strong coupling effect. When this is the roof, you can see it is tilted like this. That shows there is a roof effect will be there in all the time, most of the cases in strongly coupled spin systems. And of course, without going to the details which have been already discussed in many of the earlier 2 courses, you can find out from the intensity. This gives you the chemical J coupling, and the chemical shift separation has to be obtained by taking into account the frequency of the transitions and by using a simple curve, a simple equation like this. And AB system gives centrosymmetric 4 peaks, 2 central peaks are of identical intensity and 2 outer peaks of identical intensity. And regardless of how strong the coupling difference is in the frequencies, the outer line separation and it always gives rise to J coupling. For example, I have 4 peaks here, and outer lines 2 lines separation always gives rise to J coupling, whatever the strength of the interaction. Okay, AB spin case can have 2 limiting cases. One is in a situation where this is difference in delta delta by J is enormously large, of course AB can go to AX. And if it is extremely small, or in a situation where the chemical shift difference is 0, then AB can become A2. Remember, AB can be taken to AX by going to higher magnetic field, or also if you go to very low magnetic field and if the chemical shift difference becomes 0, it can become A2. And remember, AX to AB, AB to A2 transition is always continuous. Smoothly you can keep changing it. Okay. So, how it goes, I will show you in this graph. For example, this is the AX case where 4 lines are of equal intensity, and in this case delta nu is very much larger than J. Let us find out the situation what happens as a delta nu chemical shift difference between 2 spins A and B becomes almost smaller and smaller, are almost comparable to J coupling. You see what is happening smoothly. You can see that you can trace the curve. Outer lines start moving away and it gets reduced in the intensity, and inner lines increasing in intensity. In a situation when chemical shift difference become equal to 0, then both these lines will overlap and outer lines completely disappear. And this is the transition from AX to A2. Remember, AX can go to AB, and when the chemical shift difference becomes 0, it can go to A2. This is the example how it goes. Now, of course, it can not only chemical shift, you can also vary other things, magnetic field. If we can find out what happens, this is an example to show delta delta, we keep on reducing it and how it is happening. What is an A2 spin system? A2 spins are very strongly coupled. AB itself is strongly coupled, and A2 is even more strongly coupled. In this case of A2, what will happen is the chemical shift is delta A1 is equal to delta A2, the difference is 0, delta is 0. And J A1 A2 can be equal to 0 or need not be equal to 0. And in the case of the homonuclear A2, always you can going to get the homonuclear case because chemical shifts are always equal. Heteronuclear A2 is impossible, as similar to AB, heteronuclear AB is not possible, heteronuclear A2 is also not possible. Okay, that is because of large chemical shift difference, resonating frequencies are megahertz away apart. And what are the transitions you can see in the A2 spin system? Of course, one interesting thing you should understand, A2 has 4 energy states, beta beta, alpha alpha, but in the weakly coupled case you have beta alpha and alpha beta. But in the strongly coupled case, without going more into the details, I can say these are the 4 spin states and one of them is beta beta, this is 1 over root 20 beta alpha plus beta 1 alpha 2 and of course alpha it should be alpha 1 beta 2. Similarly, this is beta 1 alpha 2 beta 1 alpha 2 there. Of course, this should be alpha 1 beta 2, there is a mistake here, otherwise it will become 0. So, this is what it is, this is beta 1 alpha 2 alpha 1 beta 2, similarly beta 1 alpha 2 alpha 1 beta 2 are the 2 things. This is called a symmetric antisymmetric transition, these 3 are called symmetric transitions. One of the selection rules of NMR is symmetric to antisymmetric transitions are forbidden. You cannot have a transition from this to this, this to this or this to this. So, this is a single energy level separated out, there will not be any transition, whereas on the symmetric there can be transition from here to here to here, here to here is allowed. So, now let us see what happens to the situation when their coupling is 0, there is no shifting of the energy states. As I said, only when there is a coupling, then the energy levels alpha alpha gets shifted up by J by 4 and similarly alpha beta beta alpha shifted down. That is what we have been discussing for weakly coupled. Exactly like this. Now, in this case of AA equal to 0, JAA, there is no more shifting of the energy state. This is the energy level diagram and you have only 2 transitions and of identical frequencies. 2 transitions of identical frequencies will be there in the A2 case, then they will overlap and give us a single peak. And of course, transition from symmetric to antisymmetric are forbidden. That is what I said. What happens if the coupling is non-zero? Same example like we discussed for AA case. When the coupling becomes non-zero, that means JAA is greater than 0. Of course, it can be less than 0 also. I said non-zero. We have again 3 energy states which are symmetric state. And what happens, as I said, in the case when there is a coupling, these energy states are shifted up by J by 4. Okay. Whereas, antisymmetric energy state is shifted down by 3J by 4. Remember, in the case of EIX, alpha alpha and beta beta states shifted up by J by 4, alpha beta and beta alpha state both shifted down by J by 4, whereas in this example these all the 3 symmetric states are shifted up by J by 4, antisymmetric state will come down by minus 3J by 4. This is an important thing, how you get it we can work out mathematically, quantum mechanically. I am not going to the details of that, just for you to understand what is happening when there is a coupling and there is no coupling, how many peaks you are going to get. Here also only 2 transitions are allowed and transition from here to here, symmetric to antisymmetric are forbidden. You are not going to see any transitions between these 2. So, you have 2 lines of again identical frequency will be there, they will overlap and give rise to a single peak. So, whether there is a coupling GAA present or not present, in the A2 case you are going to get a singlet. This is what it is, a simple example of a tetrachlorobenzene symmetrically substituted like this, and these 2 protons are chemically equivalent and it gives us to A2 spin system and you are going to get a singlet. You understood? In principle, when the 2 protons are coupled, 2 spins are coupled, you must have 4 transitions. In the classic example of the A2, because there is no transition from symmetric to antisymmetric, we have only 2 frequencies which are identical and they overlap, gives us a singlet, and it has only 2 transitions, and outer transitions anyway is completely disappeared. Of course, you may ask me a question, what happens JAA instead of positive becomes negative? Everything is same, instead this pushing up, they will all the 3 will push down by J by 4, and instead of this pushing down, this pushes up by 3J by 4. That is all. Again transition frequencies remain same. This is what happens, and this is a classical example of an A2 spin case where there is only 2 protons are chemically equivalent, no J coupling information and only a singlet, a single peak. So, these are the example of A2. Remember, AB gives 4 peaks, 4, of course, they are not of equal intensity. 2 peaks are of equal intensity to central peak, to outer peaks are of identical intensity, but all the 4 are not same. AX has 4 peaks, all 4 of equal intensity, but A2 gives only 2 peaks, 2 transitions which are overlapped. Okay. And of course, if you go to the 3 spin case, you can think of what are the possible combinations. In the 2 spin case, you have only 3 possible combinations, A2, AB and AX. If you go to 3 spin case, you can get plenty of possible combinations. It can be A3, A2B, AB2, AA prime B, AA prime X, A2X, AX2, ABC, ABX, AXY, AMX, AB, so varieties of combinations you can think of. So, in principle, all the spin systems for a 3 spin case, depending upon the coupling strength and chemical difference, you can define. But remember, A3 gives only a single peak, whereas AB2 will give rise to 9 peaks, whereas AMX is going to give you 12 peaks, ABC gives you 15 peaks. And the type of spectrum which you see, appearance is entirely different, they are not same. So, this is how we have to understand the NMR spectrum analysis. They are all coupled spin system. Depending upon the strength of the coupling, their chemical equivalence or magnetical equivalence is there, depending upon whether the chemical shift is there or not, and what is the difference in the chemical shift, and with respect to the J coupling, we can have strongly coupled or weakly coupled spin system, and varieties of nomenclatures we can arrive at for spin case. Of course, we do not want to go into the detailed discussion of everything, because this has already been discussed n number of times. Now, we will see only energy states for the 3 energy states for 3 spins. Weakly coupled I am taking AMX. Of course, we have how many possible energy states? 3 for the 3 spins I have already discussed. For a n coupled spin system, there are 2 to the power of n energy states. So, for 2 spin we have 4 alpha alpha, alpha beta, beta alpha and beta beta. For 3 spin it is 2 cube. What are the combinations? Alpha alpha alpha, 2 alpha 1 beta, like this, and in other example we can see 2 beta 1 alpha and finally beta beta beta. So, these are the possible 8 energy states, and this is my total magnetic quantum number is 3/2, this is minus 3/2, this is all minus half and these are all plus half. So, these are the 4 possible energy states. Of course, we discussed about the possible transitions when I showed you about 3 spin case, the AMX will have 4 possible transitions. What are the 4 possible transitions? Like for example, X can have like this and X can have like 4 transitions, and A can have 4 transitions like this, and similarly M can have 4 transitions like this. So, in the weakly coupled case, remember each spin will give rise to 4 transitions, but of course, I told you, and energy spin state give rise to each of them give rise to 4 transitions, but of course, we can work out the frequencies like this. I already worked out why you have to write down the Hamiltonian for 3 case, or for 3 individual chemical shifts are there, 3 different couplings are there. You have to take all this into account and diagonalize the Hamiltonian. You will get 8/8 matrix. You have to diagonalize it and get the eigenvalues, and these are the eigen energy states. And using these, you can get the frequencies. Of course, there are in this case you can find out the difference. Which spin is, for example, 3/2 to minus 1 is allowed, plus half to minus half is allowed. You can find out what are the selection rules allowed. Accordingly, take the energies have difference between the energy states which is given. You can find out what are the 12 transitions, 4 for A, 4 for M and 4 for X. And you can find out from the center of the chemical shift, there will be 2 peaks on right side and 2 peaks on the left side. One peak moves by half of one of the coupling, other one moves by half of the other coupling. Same thing happens for the left side from the center of the chemical shift. This is true not only for proton A, also for proton M and for proton X. For example, I have 4 equal AMX, all the 4 lines of equal intensity. Let us say this is the chemical shift, and then from this to this, let us say if this is A, this could be half AM coupling and this could be half AX coupling. Similarly, this side half AM, half AX. If you go to the M spin, that will be a different one. Like that, we can work out and we show that all the 4 are allowed. Of course, I also showed you once when I was discussing the selection rule, there are 3 possibilities of all the 3 spins can flip at a time. These are called the combination. 3 combination transitions are allowed here, but the combination transitions arrive only at the sum and difference of the chemical shifts. It does not contain J information, and usually they are very weak in intensity, and it is seen only in the strongly coupled case. In the weakly coupled case, you do not see it. That is the reason why when I took the 3 weakly coupled AMX spin system, we got only 12 lines. Only if you go to analyze the ABC, all the three are strongly coupled, you will get 15 transitions including these three combination transitions. Okay. So, combination transition will not give you J coupling information, and that is what we discussed. This is a simple example of weakly coupled 3 spin case. You see, when it is weakly coupled, 4 for A, 4 for M and 4 for X, all are of equal intensity, remember. That is why we are going to see very clear spectrum, and this is the center of this, and from the center of the chemical sheet of this one, half of this is one coupling, this one is half of another coupling, this is half of other coupling, this is half of other coupling. So, from the center you have 2 peaks on the right side, 2 peaks on the left side for all of them like this. Okay. A true example of an AMX is like this. This is a 600 megahertz spectrum of 2-fluoroic acid. Remember, these are these 3 protons are very well separated in chemical shift like this, you see, A, M and X. At 600 megahertz, you see, all the 12 lines are of equal intensity. This is a real true example of an AMX case, and you go to the center of this, if you expand it, you get only 4 peaks, very easy to analyze. I told you weakly coupled cases spins, spectrum of weakly coupled spins are very easy to interpret. We can easily extract the coupling and chemical shift information for all the 3. Of course, you can come across a situation, you can think of an AMX, appears like AMX, but not AMX, because there will be a minute ABC character will be there. An example like this. Look at the example like this. This is in principle this and this are the 3 protons. You can find out very well separated, chemical shifts are very well separated. Appears like AMX because all the 4 peaks, there are no additional peaks like ABC, here no combination transitions are seen here, only 12 peaks. But really if you carefully see, they are not of equal intensity. That means there is a minute ABC contribution is there, ABC character is there, minute ABC character. That is why in principle of course you can analyze and get the J coupling information and chemical shift, but if you are a hardcore NMR spectroscopist, we do not accept it because it is still not AMX. You can't analyze. For the first order approximation it is okay, otherwise you need to still go to higher magnetic field and then make sure all the 4 lines are of equal intensity, so that you can extract the chemical shifts and the coupling information and make it weakly coupled. As I have been telling you, a strongly coupled spin will become weakly coupled when you go to higher and higher magnetic field. Why? Because chemical shift, as I told you, depends linearly on the magnetic field. If you increase the magnetic field, the chemical shift separation keeps on increasing. As a consequence, what happens? The strongly coupled spin system will become weakly coupled when you go to higher magnetic field. So, for this, if there is a tinge of a strong coupling character like this, what you are advised to do in case if you want AMX, you have to record the spectrum at a even higher magnetic field at a higher frequency NMR spectrometer. Okay, look at this one. This is again trifluorovinyl chloride, beautiful AMX case. For all practical purposes, this is a fluorine NMR. You can see all the 3 are of equal intensity. In principle should be, but there is some sort of a deviation is there in the intensity. This skewing direction tells you this is coupled to this skewing direction tells you this spin is coupled to one spin which is resonating towards its right. This direction of skewing tells you this spin is coupled to spin which is resonating towards its left, and this is a roof effect. I told you the roof effect becomes stronger and visible, more prominent in strongly coupled case. As a consequence, I do not consider this as a weakly coupled AMX. It is AMX with tinge of ABC character. What do you want to do it? If you want to make it a perfect AMX, remember fluorine was recorded at 56.4 megahertz. That means it is a very low frequency spectrometer of 80 megahertz NMR spectrometer or so. On the other hand, record this fluorine NMR at 400 megahertz, then fluorine comes at in the 400 megahertz 370 or 388 whatever that frequency, in which case what is going to happen is all the 4 lines, all the 4 lines of A, M and X all will become equal intensity. That is a true AMX. You understand? So, true AMX you will get only at higher frequency. This is another example of a molecule, a 200 megahertz spectrum which gave AMX pattern with minute ABC character. Look at this one, these 3 are protons, and it looks like there are 4 peaks here, 4 peaks here and 4 peaks here. What normally the chemist will do? They will take the NMR spectrum of this, measure this chemical shift and say, okay, I got the chemical shift and J coupling. It is okay to report to some extent, but in principle, as I told you, when the spins are strongly coupled, it is not possible to get the individual chemical shifts. You can only get the difference in chemical shifts. Individual chemical shift cannot be obtained. But in this case, we can assume for all practical purposes they are weakly coupled, and you can get the chemical shift from this one for the center of this. This one J coupling is from here to here and another J coupling is here. Like this you can extract J coupling for all these things. So, this is the way you can analyze this thing. Of course, you can go further and I continue this one. What is going to happen? I will show you a simple example how the spectrum becomes completely different when you go to higher frequency. Can you imagine, this is the spectrum of a hypothetical, not hypothetical, real molecule. There are 3 protons here with some substitution. Look at this spectrum. This is 3 spin. We have written A, B and C, but I do not know which is A, which is B and which is C. We cannot mention it easily, but for just for the sake of explanation it is written like this. And look at the number of peaks here and their intensity pattern. You cannot extract this and analyze from the center of this is A, this is B, M and X like that. You cannot do that. You have to simulate it. You have to do the computer analysis, get the real frequency of the transitions and the intensities, only then you get the chemical shifts and J coupling information. Otherwise, straightforward first order analysis is not possible. That is what I have been telling you. So, in strongly coupled case, you cannot analyze in an easy way. This is not possible. This is called second order analysis, where you need to do computer simulations for all the frequencies and all the transitions, intensities. Look at this one, 600 megahertz, very well separated peaks. Looks like ABC becomes AMX here. Strictly speaking, if I say this, if I give you this spectrum and say is it AMX, your answer should be no, because look at this intensity, they are not equal. But for all practical purposes, compared to this is easy to analyze, and you can assume this is a AMX case, there is no problem, although there is minute ABC character present in this. This is what ABC at 100 megahertz became AMX at 600 megahertz. Here this is 600 megahertz. If you really want to get a pure AMX, instead of 600 you have to go to 900 megahertz or 1 gigahertz. Then you can see all of them are really pure AMX with all equal intensity. So, strongly coupled becomes weakly coupled at higher field. This is what I just wanted to tell you about the Pople information, Pople nomenclature and spin coupled system, and I took the example of the 3 case spin case here, took AMX. But if you take ABC, what will happen? You will not get 12 peaks, you will get 15 peaks. There is no way you can analyze it in a straightforward way. What happens if I take a A3? All the things really, for example, all the 3 are chemically, there is no chemical shift difference at all. All of them hydrogen at the same frequency. There is no difference in chemical shift. Then it is A3. Will the coupling be present or not in the A3 coupled spin system? It can be present, it need not be present, does not matter, but it always gives a single peak. ABC gives 15, AMX gives 12 transitions, ABT gives 9 transitions. So, depending upon how the spins are coupled, whether strongly coupled or weakly coupled, you can get lot of different types of spectra and lot of information can be obtained by analysis. Except for AMX, no other strongly coupled cannot be analyzed in a straightforward manner. So, this is what I just want to tell you about the way we have to analyze the spin system, depending upon, and we have to, of course, lot more things can be done even in the AMX. All the 3, if you have all the, there are so many nomenclatures I gave you. If you have to analyze each of them, can be analyzed, write down the spin system, write down the Hamiltonian, diagonalize the Hamiltonian, get and then get the eigenvalues and frequencies, and then you can do simulation and get all the information. It is laborious work, it cannot be done so easily. But I do not want to discuss all those things, but I just wanted to give you an idea. You need to use the Pople nomenclature to analyze the spectrum. So, this is what I wanted to tell you about the Pople nomenclature, and next we will go to the interpretation of the real interpretation of the one dimensional NMR spectra, 2D NMR spectra, etc. later. First we will start with the 1D NMR spectral analysis, and today what we have covered already. So, from the 2 spins I said we give maximum of 4 transitions. If you have a 3 coupled spin system, we can have maximum of 15. If they have 4 coupled spin system, 56 transitions, because this is the number of transitions are given by 2nc n minus 1 is the formula. Put the n is the number of coupled spin. Put the value of n and calculate the number of transitions. As the number of spins become more and more, go to 6 spins, 792 transitions. If you go to a 7 spin, 3003 transitions you will get. So, it is very complex spectrum, but most of them are redundant. We do not require that many frequencies to get the spectral information. And then of course, I showed you an example of a 3 spin case AMX, how the transitions, 4 transitions for A, M and X are obtained just by looking at the energy level diagram, write down and get the applying the selection rules. Of course, we can calculate the eigenvalues, eigenfrequencies and get the correct frequencies. As the true intensity will be exactly 1:1:1:1 for each coupled spin system in the AMX, if we will get 12 transitions, but it is not the case with a strongly coupled case. That is what I just wanted to tell you. I will stop here. We will come back and continue with other things in the next class in the analysis of the proton NMR spectrum. Thank you.